So hello everyone and welcome. It is my pleasure to introduce Donggeun. He is the Chief AI Officer of Lunit and he's here to talk to us about the history of AI. So welcome and thank you, Donggeun.
Hi. Thank you for introduction. My name is Donggeun. I am one of co-founders of Lunit, and I am leading the AI division. And so the title was originally the history of AI, but you know, this is Lunit's place, and I'm working in Lunit, so I added Lunit within history of AI. Actually, I added Lunit because Lunit is actually being the part of the AI history. So I'm really proud of that. So the combination of Lunit and the history of AI would be smooth. So it will be, I hope this talk will give you a nice insight of how the AI works and also what's the important in AI. So through this talk, you can get the idea of very shallow but very simple idea of how the AI model works and the important thing of the AI. So let me start from the very beginning of AI model. So this is the first one. In 1950s, we called it perceptron. So this psychologist, Frank, this is the person who first introduced the first model, very initial model of AI. So in this picture, in the left, you can see this is, you can think this is a sensor, so stimulus. So from this sensor, there will be a node A1 and AI and AP, something like that. So each node, you can think, each node can have some scalar value. So A1 is a scalar value come from this stimulus. You can think in that way, yeah. So there could be many nodes. It shows only 3 nodes, but there can be many nodes. And the signal goes through this path. Here is a W, which is a weight. We call it model weight. This can also be a scalar value. And then the signals are combined here. Here is the operation is the summation. And after that, we apply some threshold. And the model produce the output value F. So this is the very simple model of AI. So if we make a mathematical formulation of this signal path, then it will look like this, right? So the stimulus A is combined with weight. Then this operation, we can think this operation as a multiplication, like this. A1, weight 1, plus A2, weight 2, plus AP and weight P. So because here is a summation, and because here is a threshold operation, I added this sigmoid function. Yeah. So this is very simple. So if the value of f is positive, then we can occur as a positive decision. And if the value of f is negative, then it's a negative decision, right? So it's a positive, then it's a cat. And negative, then it's a dog, something like that. You understand? So when we say train a model, when you say train on AI, learn on AI, that means looking for the value of W. This one. So we use many different optimization methods in originated from some optimization field. Then we can find W values. We call that training. We call that learning, right? So this is the origin, very origin of AI model. So this is 1950s, and in 1980s, so it's after 30 years after the original perceptron model. In 1980s, this is the neural network model. As you can see in the animation, it's simple stack of perceptron. That's it. This is real. Yeah. So simple stack of perceptrons. We call it neural network. And some of you may heard about backpropagation. That is just an algorithm to determine W values. So in the original perceptron model, it can be a little more easier to optimize W values because the number of W values is relatively small, right? But in this stacks, there would be much more number of W values. So we need some special algorithm to look for the W values. So we call that algorithm backpropagation. So this is the era of neural network combined with backpropagation algorithm. It's 1980s. And in 1990, people so imaging technology was emerging. So people also wanted to make some AI model for image, like this. This is a hand-digit classification problem. So in this, given this image, we make the researchers at that time. The researchers tried to make the neural network work on image in this way. So just the stack to X and Y. So let me skip some details, but you can think in this way. Stacking perceptrons to the x-axis and the y-axis, then it's a convolutional neural network. And here, this researcher, Yan-Kun, is the inventor of convolutional neural network in 1990s. So we just put this convolutional neural network between this image and this label. We train the network. Training means finding the weight values of this network. So this is the origin of the convolutional neural network. I think some of you already know this concept. So this is the original. This is the origin, but it's been very difficult to train this model actually at the time. Because you can see that starting from this perceptron, we already stacked it in this way, but in the convolutional neural network, we stack again to another axis, right? So there are too many number of weights, which means that we need much more powerful computation to look for the weight. Why? Just because there are too many weights. Yeah. So it's computationally very expensive, and it required a lot of data. But at that time, in 1990, the memory size was very small, and the storage size is also very small. And the CPU has relatively very poor performance compared to our recent computers. So it's been very difficult to optimize the huge amount of the weight. So I would say it's failed. It's failed to be used in many areas. No one in AI industry and no one in academia use convolutional neural network and neural network from 2000 because it failed to train. So in 2000, this researcher invented a very simple AI model we call SVM, Support Vector Machine. So you can think also this is a very basic formation of perceptron. You see this picture in the beginning, right? It just excluded, it just removed the threshold. You know, here. In the original slide, here is a threshold node, but in SVM, there is no threshold, just the sum, right? So very simple. But then what's the new invention? So this guy proposed a very nice, very beautiful way of finding the weight. So given the data, training on SVM, in other words, given the data, finding the weight is very, very optimal. SVM guarantees the global optimal values of weight mathematically. So it becomes very, very popular in the AI industry and AI academia. So I would say 2000 is the era of SVM. But as you can see here, compared to the neural network, the model is too simple, which means that there should be some other things that humans should do. Even though this is computationally very cheap, and even though this requires a few data points compared to the neural network, it requires a lot of human engineering, something like this. Let's see this example. The problem is to count the number of stones in this image. Let's say, our problem is to count the number of stones. Here's the image. Here's an image. Then the engineers should come up with many ideas to represent this image to the vector space. Because let's say the horizontal axis, the number of pixels here is 100 pixels. For the height, also 100 pixels. Then it means 10,000 pixels, right? then it means that the dimension of the image is 10,000 dimensions. 10,000 dimensions means we need at least 10,000 weight, right? Because in the model, yeah. For each stimulus, we need one weight, right? So in order to apply directly SVM to this image, it will be very, very difficult. So, 100 by 100 image is very small image. 1,000 by 1,000 is more general. Then it means 1 million pixels. That means 1 million weight to apply SVM. So it's not a good idea. We need to look for a better feature space, a better space to apply for the SVM. So we have to apply some human engineering, something like this. So we engineers implement an algorithm to extract edges of stone by applying some different filters. And then after extracting edges and after we filling out the contours, then we can get this kind of image, right? Yeah. And then we can make a peak inside the blob, right? That's needed. So we apply some other algorithm that something like distance transform. Then we can get this kind of image. Then we can get local peak, right? So that count the number of stones. And then we also apply some another algorithm to factorize this image. So we make a vector, a set of numbers. And then we can apply SVM. So in 2000, this is the major stream of AI development. A lot of deep engineering by human and very shallow learning by using SVM. So what if we apply neural network to this problem? So we just employ a convolutional neural network model, and there will be no human engineering, right? There will be no human engineering. Just to put this model between the image and the ground truth and train this model. It's very simple, right? Very simple. There would be almost nothing for human engineers to do, just to run the model. But the problem is that it's very expensive, computationally very expensive. And it requires a lot of data, because the number of the weights are, there are two tremendous numbers of weight. So we need computation, and also we need more data to find better weight values. That's the blocker. That's the blocker of the deep learning at the time. So I would say from 2000 and 2012, SVM took over the mainstream while deep learning was pushed out at that time. So this is interesting to see that, starting from the perceptron, the next model was neural network. Neural network is the same thing that we call deep learning these days. Neural network is the deep learning. So we can say deep learning method was already invented 30 to 40 years ago, but it's failed. In 2000s from 2000 to 2012, it was an era of SVM. So a fun thing happened at that time. You remember this guy? So Jan LeCun, who is the inventor of convolutional neural network. He tried to submit his paper, his convolutional neural network paper, to the computer vision conference. Computer vision is academia dealing with the AI for visual recognition. So we call it computer vision. So Jan LeCun tried to submit his convolutional neural network paper to CVPR, which is the name of computer vision conference, but he get rejected again and again. So he became very angry. So he decided to withdraw his paper and he boycotted CVPR. So he make this long email to the chair of CVPR, and he disclosed this email to his homepage, and he started to boycott CVPR. And as you can see in this letter, here is getting papers about feature learning. Feature learning is deep learning. Getting papers about feature learning accepted at CVPR has always been a struggle, and I had more than my share of bad reviews over the years. And the reviewers in computer vision area were clueless and negatively biased for deep learning. So actually, for around this time, I started my graduate course. So when I started my graduate course, there was no one who working in deep learning, including my professor and including my colleagues. And even when I attend conferences like CVPR, 100% is using SVM with human engineering. That's the AI at the time. No one works for deep learning. But I can understand, actually, for you, it doesn't make sense. Deep learning is a good method that minimizes human engineering, right? Deep learning is a very good method that minimizes human bias, inductive bias, while depending purely only on the data, right? So now we know it's a very good method. So you can think it doesn't make sense. The reviewers are negatively biased to the deep learning. It doesn't make sense. But I can understand why they also rejected the deep learning papers. Because according to this table, this is one of the paper published in another area, not in CVPR, ICML. So you can see like this. CDBN, this is a model of deep learning. This is a deep learning method. And it shows the performance 57, 65, right? And here is in the bottom, this method is SVM. It shows a slightly better performance compared to deep learning, right? So deep learning doesn't beat SVM. And at the same time, deep learning requires a lot more computation. So that's the reason reviewers rejected deep learning papers all the time. But you should look into this fact. Training size. So it's only 20 years ago, less than 20 years ago, it's surprising to see the number of images per class for training. 15 or 30. At the time, this is very normal data set to train AI model. So let's just say cats and dog problem. For cat, we use 30 image. For dog, we use 30 image for training. So at the time, I'm not sure why, but this was very general. So you should look into that number. Given that small amount of training image, SVM will always be better than deep learning, because SVM has much smaller amount of weight, but deep learning has a lot of weight to optimize. So then let me switch a little to Lunit. So around this time, Lunit started. So at the beginning, our company name is not Lunit. It was Cloud Designers. At the time, cloud technology is emerging. So we named our company as Cloud Designers. And we started to utilize AI method to the fashion industry. So because this is SVM area, we also followed the same paradigm. So all these are human engineering. So given this t-shirt image, we extracted t-shirt boundary and analyze the color and apply some other machine learning model like SVM. And we made this kind of product at that time. We started from fashion industry. So just to click a t-shirt, then it searches similar products. And then the customer, the user can get a link to the shopping mall where the user can buy that product. So these all are very deep human engineering and shallow model like SVM. And we can also click some pattern, and then it shows, So you may feel these days this is nothing, but at the time it was a very cool thing. And also by applying a lot of human engineering, we make this kind of a little more advanced and complicated images. So not very natural image, but we analyze the part and searches so similar cloth from the web. So engineering, human engineering. So I would say, again, 2000, it was the age of handcrafted feature, handcrafted engineering plus SVM. In the meantime, there was a professor in Stanford University. Her name is Fei Li. And she made a very large data set ImageNet dataset. You heard about this? Yeah, I think some of you know it. It's a very large dataset composed of more than 1 million images. And it also contains the label, the object classes of the image. There are 1,000 object classes, and each image is associated with an object category, object label. So, as I mentioned before, at that time, people uses this amount of training data, right? It's very small, but Fei Li argued that this is not good for AI development. We need a much larger data set for AI development. So that's the reason she make this data set and open this data set to the public. So researchers started to use this data set to train their AI model. So this is one of very big change in AI academia. And in order, so this professor also wants this data set to be widely used in the whole academia. So as a way to make it very popular, she launched a competition by using this data set. So some of you may heard about ImageNet Challenge. So that's that one. Yeah, we call it ILS VRC. ImageNet Large Scale Visual Recognition Challenge. So this is very historic challenge of AI development. So because she released this dataset in 2009, the first competition was held in 2010, and the next one is 2011. And at the time, the winning method, this is the winning method, winning of the competition, each competition. The winning method shows the error around 28, 25. And after 1 year, so at that time, all the winning method is handcrafted feature plus SVM. It's very fun to see that it's only 10 years ago. You know, now we have ChatGPT, but 10 years ago, it's handcrafted features with SVM. Yeah. What happened then? So there was one graduate student in Toronto University, and his professor is the inventor of neural network, Jeffrey Hinton. So he is one of the students of the professor. And he was a bit famous in academia because he was very good at programming. He is very nice programmer, very fast and very accurate. So he started to implement deep learning model in GPU. Yeah, that's the beginning of this ChatGPT, you know. So there was nothing new in the methodology. He just used the same convolutional neural network. The convolutional neural network was made by Yan Li-kun in 1990, yeah. So he just implemented this convolutional neural network on the GPU. Then it makes training fast, right? So because training becomes fast, we can apply more training data, right? And he trained this model by using ImageNet. And he joined the competition 2012. And it was the result. So error rate eventually become 16, around 16, which is 8% point better than the previous winner with totally new method. It's a deep learning method. We call it AlexNet. It's a very historical name. Now it's very historical. It's a kind of very typical neural network architecture composed of 8 layers of convolutional layers. So people started to confused. What is this? Still there are someone who working in deep learning, and deep learning win the competition. So AI researchers were surprised to that event. And at that time, we, Lunit, was a cloud designers. Our leader, who is now chairman of Lunit, whose name is Anthony. Anthony, right after the IRS VRC, and right after he see the result, he bought this GPU. This was GTX 580. And he started to convince me and my other teammates to use deep learning. But I resisted because I should use SVM. I am become very familiar with SVM, and I'm becoming a kind of expertise in human engineering. But he told me just to use deep learning, so I resisted. And after 1 year, there was another team also using deep learning and showed lower error in ImageNet. So there's no way for us as well. So it seems that it's very clear, in order to win in the industry, in order to win in the academia for anything, there would be no way but should accept using deep learning. So we quickly moved to deep learning method, and we decided to join the IRS VRC competition 2014, and we were 7th place. And above us, there were Google, Microsoft, Oxford, and National University of Singapore. So it was kind of, we become very proud because we were a very small team, comprising 5 people, 5 graduate students with just a single GTX 580. So at that time, the winner was Google. Google showed this architecture, GoogleNet, comprising 22 convolutional layers. And it's been 3 years after the first impact of deep learning in 2012. And after 3 years, people in academia started to move to deep learning from SVM. So this is a keyword search in Google Trend. This is a keyword search. You can see when you search deep learning, it's almost 0. After IRS VRC 2012, people started to use deep learning like this. And do you remember this guy who boycott CVPR? And he is very minor person in academia. No one like him. And he become like this. In 2015, he becomes a plenary speaker of CVPR. And at that time, he became the director of Facebook AI research. And he is still working in Facebook Meta AI. He is a chief scientist there. So it's very, changing very quickly. And Lunit decided to join the challenge again, 2015. And after submitting our result, we got this email. It was very nice email. So, dear Team Lunit guys, there at the time the number of participants are 70 teams, and the organizers told me we were invited to the challenge workshop. So we thought, oh, we may be within 1 or 2 or 3. So it was very nice email at the time, but finally we were 5th place. And above us, there was Google, and above us there were only Microsoft among these big companies. Google and Samsung and Qualcomm were lower than our score. We were very proud of that. And at that time, the winner was Microsoft. They showed 150 layers, and it's the first time to win humor performance. This is 2015. And after that, DeepMind, Google DeepMind showed AlphaGo, and it exploded, deep learning. And 2 years later, Lunit shows very encouraging result in medicine that shows the AI model beats human performance in reading chest X-ray. So, what happened? What happened? It's only within only 10 years. 10 years ago, there was SVM, and 10 years ago, academia uses tens of images for training. And after 10 years now, there is a ChatGPT, and ChatGPT trained on internet scale data, right? So what made this change? It's very simple. This one, neural network, there has been no changes in neural network. I know there are some changes, but that's detail. Overall, this is the same stack of perceptron. And this idea was invented 40 years ago. So same model still. And we are using the same algorithm for training. You remember backpropagation. ChatGPT is trained by backpropagation. The same algorithm, same model. Nothing changes in high-level view. So what changed? The scale of the data and the computation. So this is the one who showed the power of data and computation first time. And that's the trigger of this AI era. So as I mentioned, starting the presentation, I hope you may understand how AI works, and I hope you understand what's important in AI. So if we keep working on deep learning paradigm, so then it's true that the competence will be always in the computation and the data, not the model. There will be some evolution, there will be some advance in model architecture, but In high-level view, that's the detail. So you know, Google also have AI organization we call DeepMind, right? Google DeepMind Google DeepMind is composed of very talented AI researchers, graduate from top-level universities, publishing a lot of high-impact AI papers. That's the Google DeepMind. And at the same time, in the similar time, OpenAI was founded. And it was definitely true that the level of the engineers, the level of AI researchers is lower than Google DeepMind. But now OpenAI leads AI industry. It's true, right? So what happened there? Google focuses on the neural network. Google DeepMind has focused on the neural network. And as you all know, OpenAI has focused on the data and the computation. So actually, you know, ChatGPT model, in the ChatGPT model, as we call this as convolutional neural network, for ChatGPT, there is a specific name of the network architecture. We call that transformer. Actually, the transformer model was introduced by Google. And Google keep working on new architecture, new method. But OpenAI just take the transformer and they work for the data and computation. And they made ChatGPT. So I think you know what's important. So yeah, it's the same in 2020. It's the same, still same. As we already witnessed the ChatGPT. So in computer vision area, not in the language area, in computer vision area, as you can see so far, so this 1 million is the ImageNet scale, ImageNet data set for training, and this 62 million is the number of weight of the convolutional neural network. So as time goes by, we use the same training set, ImageNet, but model is also on par. The model size is also on par to each other. But in 2018, it's by Facebook. They utilized 940 million Instagram images for training. And it showed much higher performance, right? And after that, Google utilized a similar scale, 300 million images with much bigger network and showed much higher performance. No, this number directly shows what's important. So, large scale data and large scale computing. That's important in deep learning paradigm. So I hope you get good insight in AI industry. Yeah, thank you. Any questions? Yeah.
I'm curious, what made you pivot from design cloud to healthcare?
See, that's a good question. So actually, we was very. So the question is why we changed our company name from. So why we changed our product from fashion search engine to medical AI, right? So at that time, we were very very technology-oriented team. So for us, the mission, there should be some mission. There should be some problem definition to solve. But we started from the technology. We have AI technology, and we also wanted to found a company, and what problem to solve. So this was our approach. And it looks like fashion looks the most easiest domain to apply AI technology. But when we also, after launching several products, but it wasn't going well. So we tried to had some interview with users. And you know, in fashion industry, compared to, so relatively, woman is the target customer, right? Yeah. So we tried to have an interview with some our colleagues, and we realized that women really enjoying the time to search the product. The efficiency is not important. Yeah. So we decided to pivot to the medical domain because in the medical domain, it looked very clear for us. The accuracy is important. Yeah. So in the fashion industry, we concluded that accuracy isn't important. The time for searching the fashion product, itself is a good time for users. Yeah, it's not a matter of efficiency. So we just wanted to utilize our technology for improving the performance. So that's the medical domain. So that's the reason we pivoted to this domain, and I think it was very nice decision at the time. Yeah.
Where do you see the next 10 years in AI? What do you anticipate? The last 10 years are so dramatic.
Yeah. So from my perspective, if there is no new paradigm for AI methodology, then it will be more and more. How can I say it? So it's very difficult to speak in English. Jay, can you help me? 자본집약적이고, 네, 더, 그러니까, yeah. Yeah, yeah. So as you can see, yeah. So the data is money, and the computation is money. Yeah. So the competence will be more and more for the big giant tech companies like Microsoft and Google. But if the academia does their work very well, so let's say they propose a new paradigm of AI that doesn't require this amount of the data. So actually for human, I don't think we need that amount of the data. Yeah, human don't need that amount. So if academia suggests some better methodology of AI, then things can change. But if not, to me, it's clear. It's still clear. More data, more computation. That's the direction. Yeah. Anything else? Okay. Thank you for listening. Have a good time. Yeah, thank you.